Okay, so last year we have seen the volumetric strain rate, linear deformation and volumetric strain rate. Just recap this thing, and next will come the conservation of mass or continuity equation, and how these two things is related we'll see by this way. So just recap for the last topic. I'm just going to recapping this portion. Here, the linear deformation, we got that along x-axis. So along x-axis linear deformation, Exx dot rate of shear strain along x-axis. We have got this thing del u by del x. Along y-axis, the linear deformation, it is called the strain rate along x-axis. Similarly, along y-axis, we got it del v del y. And along z-axis, this strain rate is the dw dz. In this way, we can write it down, or we can be able to write it down as a u. We can write it because of this u1, v is equal to u2, and w is equal to u3. In this manner also we can write it down. Difference, there is a certain difference is there, and similarly x we can write it down x1, y is the x2, and z is the x3. In the higher advanced fluid mechanics, we are writing in this way to keep the indices term. So it is coming in this way, du1, dx1, du2, du3, del x3. So in this way we can, the same thing, same sense is going on, just replacing u1, u is as a u1, v as a u2, and w as a u3. Same way, similar way, the volumetric strain rate value, we are getting it, we write it down, the volumetric strain rate is a rate of change of volume. This is the volumetric strain rate. The change in volume by the old volume divided by the time. So volumetric strain rate, we can write it down in this way. That is, we are getting this after the derivation, we are getting the value du dx plus dv dy plus dw dz. On the same manner, we can write it down in this way, du1 dx1 del x2 y x2. It is the indices form we are taking it in this way. So it can be written as the duk d del xk, del uk del xk. Both are the same. As to the same component, it seems that there is an invisible summation is there, because as here also k, here also k, 2k is there, repeating index. As there is the presence of the repeated index, we can say, otherwise k is equal to 1 to 3 if you write it down. But this summation portion is the invisible here, according to the Einstein notation. According to the Einstein notation, this is the invisible. So simply you can write it without the summation. Simply you can able to write it in this manner. We'll see this kind of thing in the next time. Or in vector term, if we're going to write, this is the indices form. This is the indices form. And this is the most general form. Another, the vector form. In terms of the vector form, you can write it. So vector form does not depend on the coordinate, whether it is a Cartesian coordinate or cylindrical coordinate or spherical coordinate. It does not depend. Before going to the coordinate, why we choose Cartesian coordinate, why we choose cylindrical, spherical? Because the convenience of our problem. If you are given the problem as a cylinder on basis, So it is better to get the cylindrical polar coordinate. So it will be easy to solve the problem. So in such a way, we are choosing the coordinate. So vector form, in terms of the vector form, if you are writing out, so what it comes like that, del operator is, you know this in vector form, that is I d dx plus j d dy plus k del z. All are in del, sorry, not d. Del. And v function, velocity function, that is the I u plus j v plus k. If you do the dot product of this two, del and v, you will get back this del u del x, del v del y, del w del z. So the volumetric strain rate 1 by delta dv dt is the total differentiation. But here it is actually in this kind of property, we'll see later. This is the divergent. It is known as the divergent of v. So better to write it, divergent of velocity vector. So volumetric strain rate is the divergent of velocity vector. For the incompressible flow, last note is the most important. For incompressible flow, this volumetric strain rate is 0. For incompressible flow, volumetric strain rate is 0. That is the definition of the incompressible flow. So divergent of V is equal to 0. That is the one and only definition of the volumetric strain rate. Now we'll see the continuity equation here, conservation of mass. So mass is conserved, we know. Over a system, the mass is a conserved. So our system approach we are taking first. So first approach we are going to take, that is the system approach. So it's we are taking system approach. So in the system approach, we know things. The mass is equal to rho is the density into volume. There is no doubt about it from the definition. We're getting it. If you take the natural log in both sides, ln m is equal to ln rho plus ln volume. Then you differentiate this thing with respect to the time. You differentiate both sides with respect to the time. But here, the differentiation, you have to invoke the total differentiation. Keep it in mind. You are invoking here the total differentiation. Why? Because the control mass approach, you have seen the Lagrangian approach. If you invoking the total differentiation, you can be converted in terms of the Eulerian description. So that's why to convert this thing in the Eulerian, because we know that the Lagrangian approach and Lagrangian description and Eulerian description are interconvertible. So we are making it in this way. So we're invoking here the total differentiation or material differentiation, material derivative or substantial derivative. So many names is here. So 1 by em by dt, 1 by rho d rho by dt, 1 by v del v by dt. Now hope you can understand this thing is the volumetric strain rate. You have seen here the definition of the volumetric strain rate is given in this. So this is nothing but volumetric strain rate. Strain rate. Now we know control mass system, where mass in a system, what is the definition of the system? Fixed mass and identity. Fixed mass and identity is the definition of the system. So here, the control mass system, this term is automatically zero. So no change in mass. So this is automatically, it becomes a zero. Zero is equal to 1 by rho, d rho by dt, plus 1 by v. Before going to any calculation, I'm just telling you here, if it is an incompressible, if the flow is an incompressible, mostly water, everything is the incompressible we are considering, this liquid, if it is an incompressible flow. So we know the case incompressible, the volumetric strain rate is zero. As the volumetric strain rate is zero, so from this equation we are getting that the total material derivative of the rho is equal to zero. Material derivative of the rho is equal to zero. What is the material derivative? If you remember the material derivative last lecture, I have told you that is the del T plus, whether you remember in Cartesian coordinate we are writing it down, u ddx v dy plus w del z. So del by del T, u del x, v del y, w del z. That is the actual cases. So if you write it down, del rho del x plus so incompressible flow, that is the equation. If rho is equal to constant, then this term must be zero. So rho is not varying with the t, rho is not varying with x, y, z. So this is a constant density flow. But all constant density flow is not an incompressible flow. All constant density flow is incompressible flow. But incompressible flow does not mean that the constant density flow. How it is like that? Because the summation, if density is not a constant, if density is the function of something x, y, z, something, density is a function of some location, spatial function. And after doing this operation, you are getting ultimate value is zero. Then also it is satisfying the incompressible flow equation. So density need not to be zero in case of the incompressible flow. But if density is constant, so density need not to be constant. I'm again telling, density need not to be constant for the case of the incompressible flow. Density may vary, but the summation, this summation should become zero. It is arranging in this way, so the summation becomes zero. So whether density is a constant or density is a variable. But if it is satisfying this equation, it is an incompressible flow. So incompressible flow does not mean the density constant. Density constant is a part of the incompressible flow. That's something. So in this sense, some example that like the molten metal flow. So molten metal flow, the density is changing, but the flow is an incompressible flow. That is one example. Now here, if it is not an incompressible flow, so if you are considering again, so this equation I am rewriting again. This equation I'm rewriting again, but I hope you got the concept. Incompressible flow is the most important concept. Incompressible flow means the volumetric strain rate is zero. That means here you are getting this equation. Del rho. So in the continuity equation, when we are writing the incompressible flow for the continuity equation, that is, this is enough. Or divergent of V is equal to 0 is the continuity equation. Because it is already 0, it is already anyone, you can write it down. So normally we are writing this equation. Del U del X plus del V del Y plus del W del Z is equal to 0. That is the continuity equation for incompressible flow. That is the continuity equation for incompressible flow. Okay. What does it mean by the continuity equation? Because the existence of the flow field, you can verify. If you are given some velocity, some x, y, you know the velocity vector. So you know the u, v, and w. And if you verify this value, if it is satisfying, this equation is satisfying, and flow is incompressible always. So there is the existence of the flow field. Existencing. The flow field is existent of flow field. Okay, so it will give the existence of the flow. So again, I am rewriting this equation if it is not an incompressible flow. If it is a compressible flow. For the general case, we'll see what is the equation is coming. This equation is only valid for incompressible. Mostly all liquid might be covering here. But if the flow is not incompressible, then what would be the condition? So we are rewriting this thing, whatever we are getting from this equation, we are getting this thing that del rho by del T, 1 by rho, plus 1 by V, dV by dt. So d rho by dt plus 1 by V, dV by dt. So that is nothing but again this writing 1 by rho d by dt plus divergent of V. Divergent of V is equal to 0. If you take the rho in this side, rho into divergent of V. So if you split up this thing, so already you have seen del rho by del T plus U del rho by del X plus V, Cartesian coordinate, we are writing it down. Del rho by del X, del Y plus W del rho by del Z plus rho into du dx plus tv dy plus dw. Okay. Now this part and this part you separate in this way. So what you are getting? Del rho by del T is keep it out, and u del rho by del x plus rho del u by del x. Similarly, v del rho by del y plus rho del v by del y plus w del rho by del z plus rho del w by del z. What does it mean? This is, we are writing the final equation here, dp dt plus d dx of del x of rho u plus del y of rho v plus del z of rho w. That is the final equation, final continuity equation. It is a generalized continuity equation in Cartesian coordinate. In Cartesian coordinate, where along x-axis velocity u, y-axis v, and z-axis w. If any flow field should satisfy this equation, then only it will commence the existence of the flow field. Any problem if you are giving u, v, and w is given to you, you have to check that whether it is satisfying the continuity equation or not. If it is not satisfying the continuity equation, it means that there is no existence of the flow field. So that is the equation. That is the final equation. If it is a steady flow, in case of the steady flow, so this part del rho should be, this part will be remaining part. Steady flow. So steady flow equation will comes in this way, del x of rho u this way. So it is better to write it in the vector form. If you write it down, divergent of density into it is equal to, that is a steady flow equation. It's a steady flow. So steady flow equation, because this part will be 0 and this part will be remaining. Already we have seen you how to write the divergent of rho is not a vector, it's a scalar quantity, but it is a varying quantity. That's why it is inside the divergent. If rho is constant, it will keep out. If rho is a constant, for constant density flow, the same incompressible equation will come back. So all constant density flow is a incompressible flow. But all incompressible flow is not a constant density flow. So varying density also, there may be chance of the incompressible flow when it's satisfying this equation. We have already told. That is the most important equation we have already told. Now, this approach, the same equation will be arrived from the control volume approach also. I will just give you some, that is the another way to, normally, that is the another way to say about this thing. I am not going in details, just give you some idea how to solve this derivation, because a lot of derivations is here. The control volume approach, what is the control volume approach? Whatever the mass is coming inside the control volume, that is your control volume. This part is your control volume. So whatever the mass is coming inside the control volume, rate of mass flow rate. So how much mass of flow is coming inside minus how much mass is going outside will gives you. So if it is equal, we can say it is a steady condition, steady state. If it is not equal, means inside some mass accumulation or reduction is happening. So this can be written as the del M of CV, control volume mass is changing with respect to time. That is the equation. Whatever the mass is coming inside to the control volume, and whatever the mass flow rate is the mass flow rate. Mass flow rate is coming inside, mass flow rate is going outside. The balancing part is increasing the mass of the control volume or decreasing the mass of the control volume. That is the condition in here. So along x-axis mass flow rate, along y-axis mass flow rate, along z-axis mass flow rate, we have to finding out, and we have to do this operation this way. That is the another approach to getting this control volume approach. Previous one was the control mass approach, simple way. From the Lagrangian concept, we are convert into the Eulerian concept, or we are doing it. Here it is a purely Eulerian concept, control volume approach we are taking. What is the beauty of this thing? That is the, we are invoking here one partial differentiation. Why it is for the partial differentiation? Because the fluid is in motion condition. So to take the partial differentiation, the idea is we freezing the coordinate system. So we freeze the spatial coordinate. We freezing the spatial coordinate system. Now we are, after freezing it, now we are going to see what is the change with the time. Echo, with respect to the time, what is the change inside the control form? So we x, y, z, along x, y, z, we are fixing it. And partial differential, we're freezing it for the coordinates, fixed coordinate. We are making it such a fixed coordinate. And now we are seeing what is the change is going on. Why I am taking this approach? Because this approach will gives you the idea how to get the, this approach will gives you an idea how to get the things in different coordinate system also. I'll not explain, I'll give you the clue of the, for the cylindrical coordinate system also, the same way. And you try this thing in your ways. So this is the x coordinate, y coordinate, z coordinate. So mass in, what is the mass is coming inside? So along x-axis, u is the velocity. So we are just considering now along x-axis. Along x-axis. How much mass is coming inside? So here the velocity is u. So definitely it is the del x. So here velocity will be not u. Here's something different. What is that? U plus del u del x plus higher order terms. Because according u is a function of x. It is not a uniform. U is a function of x. Along with the x, u is changing. And that is a change along with the, like the Taylor series expansion. That is the velocity. What is the flow rate? So flow rate is the velocity into this area. So this is del y, this is del z. So this area is the u, del y, del z. Here also del y. Okay. So that is the flow rate. What is the mass flow rate? Into density. Here also. So mass in along x-axis and mass out along x-axis. We're considering. So mass in minus mass out. What is that thing is coming? That is the minus du dx rho del x del y del z. That is the mass coming in. If rho is not a, if the rho here, rho is also spatial, it depends on the space. Rho is also depending on the space. So in such a case, how you write it this thing? You write it this thing in this way. Just if rho is also the variation in the density with the space coordinate. So in that case, how you will write this thing? You write this equation in this way. You write this part. So rho u both are varying with the x. So d of rho u dx. So rho u plus this thing plus error terms into dy. Rho may be the vary with the x coordinate because the density might not be constant. It is a spatial variation. It may be the time variation. So that is a general case. So in such a case, this mass in minus mass out, if you do it, this will comes in this way. Rho u. Okay. It is a along x-axis. It's a along x-axis. Along y-axis, The same thing will come, the total along y-axis. The same way it will come. So along y-axis this side, rho v del x del z. From here it is coming out. So rho v plus d rho v by dy del y into del x del z. The same way, so we can write it down, mass in minus mass out about the del x del y del z. Along y-axis. Along z-axis, the same term we are writing it, rho w, rho z, del y, del x del y del z. This is the mass in minus mass out. What is the mass of the control volume? The mass of the control volume, only considering mass of the control volume, density into volume. What is the volume? Del x del y del z. The rate of change of the del of mv, what is the control volume mass is changing? The control volume mass is changing in this way. The volume is the arbitrary, so that's why it does not vary with anything. It's the arbitrary volume. It does not vary with anything. You may ask that there is a higher order terms, but higher order terms will comes in terms of the del, because it is the del x is there. So in terms of del x square, del x cube, but in that case, after the case, we try to convert this control volume as low as possible, as minimum as possible. So in such a way, we're trying to control volume in this way. Del x should be tends to 0, del y tends to 0, del z tends to 0. We're trying to converge this thing because it's arbitrary part. We're trying to finding out in the differential form. Differential equation always valid for a point. That's the thing. That is the idea here. So this thing should be equal to this part. So this portion and this portion will be equal. So if you write it down, this equal equation here. So what it is coming? The d rho by dt del x del y del z should be equal to the del u dx along x-axis, along y-axis, along z-axis. So this will be cancelled out. Volume is the arbitrary. Higher order terms we are not considering. Higher order terms also. If you take the volume, if you here, because differential equation is valid for a point, so it converts this part in this way. So ultimately your equation will be reached as a same equation you will get back by this analysis. So your equation. So continuity equation. You think about one thing, that is the continuity equation. Whenever we are asked in any exam, we are writing in this way, though, in this way. Rho into area into volume is equal to in some section in a pipeline, whether it is a nozzle, here we apply that, it is a section 1, it is a section 2. Rho 1 A1 V1 is equal to rho 2 A2 V2. We are writing it sometimes. What is the idea behind it by writing this kind of equation? It is a differential form, but sometimes we are writing it this way. So this thing we are getting from the integral approach. How this integral approach we will see now. This kind of thing, first of all, first thing is the one-dimensional flow. The flow is one-dimensional here. One-dimensional flow. Second consideration for taking is the steady. There is no steady, it is a steady part. So No temporal part is here in this equation. So this kind of the integral approach, if you consider here one, and you take one diffuser or any nozzle, you can take pipelines. Is a section 1. Section 1 is a section 2. So consideration is the one dimension plus steady. So steady flow equation, if you remember the steady flow equation we are writing, del rho v is equal to C. It is a steady flow equation. And it is a one dimensional. So one dimensional means only this part is there. The along x-axis part is available. So this is the equation in your hand. So such kind of cases, if you consider one small volume here, you consider one small volume dV. Small volume. So integration of del x rho u into dV, integration over the control volume. Over the control volume, this is the equation, integral approach. Now, one part is the Gauss divergence theorem. So Gauss divergence theorem is telling is the from integration from control volume to we can change in the control surface or vice versa in the Gauss divergence. How to change this kind of thing? Here, the control volume approach, if it is in form of the divergent, if it is there, any vector quantity divergent, if it is there, if you change in the control surface, so it will come simply B dot, you have to choose one surface here. From volume integral to area integral, you will change. This equation will come in this manner. Because this is the divergent part. So divergent part will be not there, and area. Area is considered the control surface. Over the control surface, if you take the surface, any control surface if you are taking, over the surface is the dA part. Over the dA, the vector, area vector, outward of the control volume. That is the N. So this volume, control volume integral, we are converting into the control surface. So we can write it down, rho v, the unit vector of area into magnitude of the area, small area. So here, how many surfaces there? This is the surface number 1, where it is the inlet. The inlet surface. There is some outlet surface or surface number 2. And this part, other of the body, from where no mass transfer is taking place. So mass transfer is through inlet and outlet. These two surface, control surface, we are considering here. Because other than inlet and outlet, there is no mass transfer through this portion. Through this portion, there is no mass transfer. Through this portion also, there is no mass transfer. So only mass transfer is happening here. So U is in this direction. Here also getting out. So U1 might be from here, it is getting out. Some short of cases. I'm not U1, U2, we'll write it later. Just U. It's not U1, U2, it's just U. So whatever the velocity is coming in this side, thus here also the velocity is going. So from the inlet, if you consider the inlet surface. So inlet surface I'm considering. Inlet surface. So inlet surface from the, what is your control volume? This part is your control volume. You have to choose the control volume. This is your control volume. This is your control volume. So from the inlet part, the area vector is outwards, minus I direction. From here, because in this surface, outward of the control surface. So that is the minus I direction. And U is UI. So first inlet section, if you write it down, U into I, theta is the minus I into TA. That is the section 1. For the outlet surface, UI, because U is in this direction, positive x-axis direction. But here, from the surface, that is also the same direction, I direction. Eta is the, here also I. Here I, here eta is the minus I. Why minus I? Outward from the surface. Here outward is positive x direction. Here outward is negative x direction. That is a change. So I, because from the 3 there is no mass transfer is occurring. So this equation can be written as the rho UDA at section 1 is a minus, in form of minus it will come. So minus plus at section 2 rho UDA is equal to 0. Okay. Now the rho might not change with the section, area of the section. Rho is not changed according to the sectional area. So rho you can keep out of the integration. So rho UDA at section 1 plus rho UDA at section 2. Rho is not changing with the section dA, but rho might be changed with along x-axis, y-axis. So it's a separate rho, but it is not a function of area. So rho 1 you can write it here, rho 2 also, no matter. It's a no matter here. Because rho may be variable, but rho is not varying with the dA, sectional area. In the same section, might not change. It may be varying along x-axis, but not y-axis or z-axis. This is the sense. So you're writing it down, rho 1 UDA at section 1, rho 2 UDA at section. What is that thing? This thing we are rewriting again. This thing, the integration of UDA over any section is equal to the average U into the section area. So UA into A. So average. The average. So rho 1 U average, U1 average into A1. Rho 2 U2 average into A2. That is the equation we are writing normally. But it is valid for only one-dimensional steady flow. First thing, first assumption. Second assumption, it is a area average. It is a area average velocity. Velocity might not be the same across the area. If the slip is occurring, the velocity might not be. So this is for this equation. Whenever we are taking this equation, it is only applicable for the one-dimensional steady flow, and the velocity is the average velocity over the section. This consideration you might have done it. In the case of the cylindrical polar coordinate, I just give you the sense, nothing else. The control volume approach through you can do it. I am just giving you some clue about this control volume approach. Why it is important? Because this kind of the cylindrical polar coordinate continuity equation, it will be enormous application in different places. You will see the Hagen-Poiseuille equation when you solve or some other equation, some planar vortex flow. Whenever you are going to solve this kind of equation, might have required. So it is better to remind something. You cannot derive all the time, but you can remind this thing, control volume approach. But I just give you the sense same way, how to getting this thing. Here you consider one section. The radial. Increase it. Extended the portion. Is the at R. Polar coordinate system. Some elemental area you are taking it. So is the R is a theta. D theta or something else. Is a dr. Is it R at R? D theta dr you take. So this is the R dr. This part, the length is the R. Or d theta or del theta, whatever, taking it. And Z, cylindrical polar coordinate means three part, R, theta, and Z. A cylinder. Same. Same way. The element is like this. This element we have taken. This is dz. Dr, r, d theta, dz. Or del r in terms of the del r or dr, whatever you can take. If you are interested to take in del r, so del r is del r, del theta, del z. Small element from area. Now the consideration is the same. Along this the direction. This direction is the r direction. This direction is the r direction. This top to bottom direction is the z direction. And over the surface, this direction is the theta direction, tangential. Theta direction is the tangential part. So radial part, tangential part, or axial. Hope you have got it. Radial, tangential, axial. That is the consideration we are taking. Okay. Now the thing is coming in this way. What is the velocity here at radial part? So at the radial part, at along r, the velocity is vr. Along theta, velocity is v theta. Along z, velocity is vz. Same like this. Okay. So here, what is the mass flow rate? So along radially means this direction we are going. So what is the mass flow rate? Mass flow rate is rho vr. Vr is the so density into vr into this area, this part area. Area is the r d theta into dz. R del theta. So the flow rate into density, flow rate into density, mass flow rate. That's the mass in. What is the mass out from that portion? So mass out from that portion is the del r. It is the variation is along r axis. Del r of this total term. But this is the total part. Actually, we are writing it in this way. It will give you a better idea. Total part. This part plus total part. Del theta del z plus the variation of the total part plus higher order terms. That is the way to write things. But here you see one thing. this part, del theta, del z is not a variable of r. So it will come out of the integration, but this r will not come out of the integration of differentiation. This r will not come out of the differentiation. So if you write it this thing, again I'm rewriting this part, just try to understand this part. Actually we are writing whatever this value plus ddr of this same value plus of higher order terms. That is the way to write. It is variation with along r direction. So del r. It is a variation along del r. So here one del r. So this is the way to write these things. Okay. So what is that? Mass in minus mass out along r direction, what will come? So along r direction, mass in minus mass out will come minus ddr, because this part is the same, so it will cancel out. Remaining part will be inside the integration. Here into r, del r, del theta, del z will come out of it. That is the along r direction. That is the along r direction. Similarly, the theta direction also, you can write it down. Rho v theta. What is that area? This part area. If you think here, you think this part area. What is that? That is the del r into dz. So del r into dz. So you can write it down here. So v theta into del r del z. Same way, what is the coming out from just opposite side? That is this part, rho v theta del r del z plus d theta of total term plus higher order terms. We are not considering here higher order terms. So hence the along theta direction, this will comes minus d theta of rho v theta del r del theta. This is along the theta direction. Same way is along the this z direction. If you are considering, if the along z direction, if you are considering here rho vz, what is that area? R del theta into del r. R del theta into del r. Same way, this is the same integration will come this part into dtz. So minus d dz of dvz r del theta del r. Variation is along z. So this is the total part M in minus M out. That should be equal to the EDT of mass of the control volume. So what is the mass of the control volume? Density into volume. So volume is, what is the volume? R del theta. It's a small elemental area. As it is small elemental area. So this part is just looks like a parallelogram. This part into, that is the equation will comes in this manner. So that is the ultimate M in minus M out is equal to the change. So hence your equation, final equation, I'm writing it down. Final equation, del rho by del t plus, to take here common, what the things you have to take the common. So r d theta del r. So here if you want any r, so 1 by r you have to put here. One inside outside, 1 by r. Similarly, here if you want any r, so 1 by r you have to. So then r will be cancelled out. So 1 by R ddr of rho dr into R plus 1 by R d theta of rho v theta plus d dz of rho dz. That is the continuity equation for the cylindrical polar coordinate system. That is the way we are getting this thing. So that's all about the continuity equation. The same way, same manner, we just keep in mind what is the mass inside, what is the mass outside, along x-axis, along y-axis, along z-axis for the cartesian coordinate, for the cylindrical coordinate, along r, along theta, along z. This thing, if you keep in mind, any kind of the continuity equation, you can solve it. So here we'll complete the continuity equation part. Next thing we'll see the angular deformation in the next video.